So in this video, we'll be doing another flywheel problem. So by now you should know that they almost look the same. You're always going to have some KE integrated from theta omega max to theta omega mean, and then we'll be integrating torque max or torque load all over, minus torque average d theta. Then from here we'll have these are formulas that we need, is equals to Ke, the very same Ke, kinetic energy, Cf, that's a coefficient of fluctuation. It's how the torque of, let me say, speed of the thingy changes over time. That is average squared. So once they say they want to determine the dimensions or whatever, so they're obviously up for this one because this one has dimensions built in it, initial, moment of inertia, right? Then okay, let's read the problem. I haven't. So the load torque in a power press is given below for one cycle operation of a press, and then we already know that our max is this one, our mean is 0, but we want to find our average. Obviously our average will be going somewhere here. Let me call it T average, make that an H. Okay, the press cycle has 40 times cycles, so it's 40 cycles per minute. So I think if we're converting that to, it will be 40 times 2 pi over 60, if I'm not mistaken. So after computing that, we got some 41888 radian per second, of which is our omega average, or average angular velocity. And then should not use more than 10% of flywheel energy each stroke. The cylindrical, so it's cylindrical, so it has some sort of thickness. I'm just bad in drawing. This is our flywheel. The thickness here, it's given to be 200 mm. Okay, it's made of of this material with this density, determine dimensions. Okay, cool. So we're good to go. So where do we start? We start here, and here we have a lot of things we don't know. Okay, so I think it's worth noting that top average, just look at it as like an area all over 2 pi. Okay, so what is our area here? When I say area, I mean this blue area. Okay, let me get it proper. This blue area. Okay, so I can just go in there so that my computations become clear for you. So I hope it is big enough. So we said our torque average is going to be literally area all over 2 pi. What is our area here? Area of a triangle is half base times height all over 2 pi. And then what is half? Half is half. What is base? Base is here. So we can tell here our base is supposed to be this minus this, which is also pi over 2. And our height is this one. So that is 1.8. 1.8 all over 2 pi. Then from here you can get your average torque and then after calculating I'm getting 0.25 torque is nm, right? Cool. So we already have this. Now we want this. This is just the max, of which is 1.8 here. This is 0.225. Oh, now our problem is our boundaries, integral boundaries. So let me say here I'm cutting in here. Let me remove all of that. I'm cutting through here for my average torque. So I'm integrating from here to here, where the max starts and where the mean starts. Let me put it like that. So I don't really know what is the angle here. Oh, this one I know it's pi. Just don't know what is this one. So I can do a little bit of trigonometry, I think. Let me just remove this and go in there and try to do some trigonometry. I hope trigonometry will work for me in there. I went close up again, and then I'm cutting my thing here, and I'm calling this line AB. Okay, let me call this one C, D, E. So from proportion and trigonometry, it's not a really big deal. We know this one is max, so it's 1.8. We also know dimensions of a bigger one, of which is half pi here. And then if you want to find this, it doesn't look that hard. We can just say the big one, the bigger height, of which is 1.8, all over the height of a small triangle. This is the small triangle that we're doing proportion of. This one is going to be 1.8 minus 225, because we are subtracting with the average. Remember, the average was a line here, which was 0.225. Okay, so this was like big all over small. So this side is supposed to do big all over small also. So big here on this side, looking here, it's this all over this. What is this? Bottom we have pi all over 2 all over small. Small is change in theta that we interested in. So you could have done the proper, I forgot, I was supposed to do the proper proportion thingy. I would have said CE all over CP is equals to big DE all over AB. So this is my proportion formula. Then it's give back to this, and from here you can cross multiply and get this one to be, let me compute. So I'm getting an answer of 1.7344. let me check if I can get it with pi so it's easy to write. So that's literally 7 all over 16 pi. So it's still not easy for me. What if I do 7 divided by 16 alone? I'm getting 0.4375 pi. That's a good one. I like that. Here we got our t. That's not enough. That's too small now. Go up a little. We have our t average, of which it was 0.225. We have our change in theta, of which it's going to be, we just got 0.4375 pi. That's there. Okay, and now we can integrate to get KE. If we do integrate, we'll get something like from theta omega max to theta omega mean of change in torques, because here it will be torque minus a load all over torque average, and we can just do that math here. That's going to be 1.8 minus 0.225. Can plug it here. d theta, remember, and then okay, so then after doing the integral here with all these numbers, you'll get 1/2 change in theta, change in torque, of which you already know, change in torque, change in theta already know, and then we can just plug in here. This one is going to be 0.4375 pi, and whatever that we get here, so change in torque 1.8 of fluctuation minus 0.225, and then I'll compute here, then get my current. I don't know what I did, but now I got the answer. I've been punching a couple of times in the calculator, pause the video, I didn't know why I'm getting wrong answers, and now I think I've come to this conclusion. Energy is in nms. Okay, so we can move on now. We have energy, we have average torque. There's also a formula that I put up there that we haven't used. We have I is equals to KE all over CF the omega average squared. In this formula we have a couple of problems. We don't know U, we don't know U. Okay, that means we have to find this one. And also we have a formula for coefficient of fluctuation. It's fluctuation, it's a matter of how the velocity changes, so obviously we have to relate to velocity. If you guess that, you guess right, so I'll just write it so that you can. Okay, CF is going to equals to 2 omega max minus omega mean all over omega max plus omega mean close. So this is a ratio, no units, but now there are more stuff we don't know here. We don't know all these omega that I've been writing. These are the means, these are means, and then these are max. Take a difference, then take a sum, then times by 2. Okay, but they did tell us something, that this thing can only use 10% of the energy. So the energy in the kinetic energy minimum, I'm going to write a statement and then explain it after. It's equals to 0.9 kinetic energy max. Okay, so we have to accept the fact that here we're talking about energy that is stored in the flywheel, right? So if the system is using 10% of the energy, that means in a flywheel now is storing 90%. That's why you see that 0.9. So I think that the only mystery was there in the question. Other than that, we are good to go. We know that it's going to be half moment omega squared mean is equals to 0.9 half. There's supposed to be a half mean omega max now squared, but everything in here is literally the same. This is the same as this one, this is the same as that one, this is not the same, and there's a one here is not the same as that 0.9. so we can solve for mean. On this case we're saying if the other one is 1, okay, let me just say that, you'll see it. Okay, then let me add more page. Then omega mean is going to equal to 0, everything cancelled here, going to equal to 0.9 under root of omega max. And if I compute this, I'll get some very long numbers, 0.948683291. Just like writing long numbers. I know I shouldn't. That is still in omega max. So now these things are giving us not exactly the values for these, but they're literally showing us the proportion. If this is 1, and this will be this much of this. So if we come back here, this is also a proportion formula. You don't really need to know what is omega mean and what is omega max. We just need to know their proportion and how they are related to each other, and this formula does very good job in that. So I'll say if this is 1, then this will be this much. So simple as that. Or if this is 1, then this will be the other much of that one. So that's what we're doing. So 2, so I'll say what if my max is 1? If I put 1 here, and if omega max is equals to 1, then omega mean is going to be whatever that is the coefficient here, 948 blah blah blah. Okay, so that's what I'm doing here, because I'm doing proportion, no actual numbers. Okay, then if mean is 1, this will be whatever that was the coefficient, 9487 onwards, and this is going to be 1 plus 09487 onwards, and then I'll get my CF to be 0.0527. Also take note, if this number becomes too big, you should question your math. So far I think we're getting quite fair answers. We now, what were we doing exactly? Okay, we're not here, we were here. We had everything except one thing, CF. So now we have CF. We can continue with that formula now. Okay, so IM is going to kinetic energy. We have it somewhere. I remember calculating it. It was this very long number, 1082 all over CF. We just calculated CF now, 0.052. Omega average squared, we had that. I don't know where we have it, but I remember seeing it here. It was 4188. Remember, it is squared 4188. That is all squared, and that will lead us to getting our moment of inertia. And then compute here. Let me try punching it on my calculator so that I can give you the proper value. Okay, then I'm getting 1.1705 kgm squared. Okay, now we have that. We are there, and then we want dimensions. You know, this IM has more information about dimensions embedded in him. For instance, we know that md squared all over 8 is our moment of inertia. And what else do we know? We know that mass, not going to derive this formula again and again. We know that mass is equals to density V. We know V density, then V will be your area of this thing, to pi r squared, not pi 2 pi r squared multiplied by some thickness. I don't remember what we were looking for in the question, but I know that I have to write that 1 times the. Okay, cool. So for uniform purposes, I can say pi, then I'll have r, not r, I want to do d squared all over 4, so that I'll have times thickness, then I'll have another d squared, then you see there I will have d4 all over 4 times thickness. So I can go back to the formula and check what was required, but we are done with the question. I don't have to solve it. There's density, they want dimensions, did they give us thickness, they gave us thickness. So it's a matter of me plugging in whatever that I have and getting what they want. So I already know mi here. After doing proper substitution, you'll get your radius to be 295 all over 2. That's 5. These are in mm's. Okay, so then your d just 295 mm's. So you can test yourself here, do some proper substitution. So I'll make a video very longer than it is already, and then you should get the same answer as this one. Thank you.